Hi, it's Mrs. T. Right now we're going to do a video on aim number 2, and so you should make sure that you are in your physical behavior of matter packet, and that while you're in that packet you turn to the page where it says aim number 2. And the aim of today's lesson is talking about how do we use temperature as an indirect measure of heat. So temperature measures the average kinetic energy. You need to marry those two terms together, temperature and average kinetic energy, and that will help you as you go along. Now, heat will always flow between objects. It will always flow from an object with higher temperature to an object with lower temperature. We measure temperature with a thermometer. And I'm sure you've seen thermometers. We have regular thermometers that are made of glass. We have digital thermometers. And if you're watching this during COVID, you probably came into the building this morning. If you did, or you've been taken into different appointments and things like that, where they take your temperature with a thermometer first. Now, this average kinetic energy is sort of related to the speed of molecules, but their speed is based on not just temperature, it's also based on other factors as well. So it's related to speed, but it's not just about the speed. Now, if I were to give you a thermometer that had no lines on it at all, and all it had was the liquid that can move up and down, what I'd like for you to do is take about 5 minutes to try to brainstorm or think about what you could do with this thermometer to try to figure out what the different temperature points are on this thermometer. And if you are watching this video and you are a hybrid student or an in-class student, what I'm going to do right now is actually pause the video so that you have that time. And rather than have 5 minutes of dead air, I'm going to pause the video, and I'd like for you to think about what you can do to get the temperature markers on a thermometer that has all the pieces, the glass, the alcohol inside, everything, but it just doesn't have, it's like as if I took a alcohol and acetone and just wiped off all the numbers and all the lines. Okay, so now that you've had a little bit of time to think about it, what we could do is we could actually take this thermometer and we could put it into a beaker, and we could put it into a beaker of boiling water and mark off where the temperature is when it's in boiling water, and then we can put it into a beaker that is filled with ice water and mark those temperatures off, because we know that at standard pressure, at standard atmospheric pressure at sea level, boiling water would give us the 100 degrees Celsius mark, and ice water would give us the 0 degrees Celsius mark. We could then divide the lines between them equally and have the thermometer work for anything that's 0 to 100 degrees Celsius. I didn't mean to move the page up, sorry about that. We call these 2 points on the thermometer, we call them the fixed points, because those numbers are known, and we could use that to calibrate any thermometer. The Kelvin temperature scale is called the absolute temperature scale, and that's because if temperature measures average kinetic energy, and average kinetic energy has something to do with the speed and motion of the molecules, at 0 degrees we should have no motion. But at 0 degrees Celsius, we know that there is still molecular motion. But at 0 Kelvin, theoretically, we get to the point where there is no kinetic energy. So we call 0 Kelvin absolute zero. And at that temperature, we would expect there to be, based on different graphing extrapolations that have been done by scientists, they would expect that there would be zero kinetic energy at this particular temperature. At this point, I'll ask you to take out your reference table. Everybody who's been in the classroom should have one already. If you're a fully virtual student, you should go to Google Classroom, and it would be a really good idea to print one out and staple it together so that you have the paper copy to look through. Now, on table T, which is the very last table, we have a formula down at the bottom that says temperature, and it says K equals degrees C plus 273. The Kelvin temperature scale is just a shifting of the Celsius temperature scale so that at 0 kelvins you have that absolute zero temperature. So what we're going to practice, and you'll need to take out a calculator, is converting between the Celsius and the Kelvin temperature scales. So what we're going to do, we're going to look at this little chart here, and if you're given a temperature in Celsius, you plug it in here, and then the answer that you get would be the Kelvin temperature. So for example, this one equals 323 Kelvin. You always have to put the unit there. But if we want to do 65 kelvins, then you put the Kelvin temperature in and you put in X, sorry about that, you put in X as your degrees Celsius. And so now we have a little bit more algebra to do here. And to get the X by itself, we're going to subtract 273 from both sides. And when you do 65 minus 273 on your calculator, you'll notice that you get a negative number. And we were converting to Celsius, so this is negative 208 degrees Celsius. So what I'm going to ask you to do, or what I'm going to do in the classroom, is pause for a few minutes so that I make sure and give you some time, and you are going to go through all of these problems on the side yourself. I will unpause to go over it. So here I am, I'm back, and I'm just going to put the answers up over here. Again, if you have not completed these answers yet, you should pause the video if you're watching this on your own. Okay, if you're watching it in class, I will have already paused it and unpaused it for you. If you're a virtual student who's watching it live streaming, hopefully this has already happened. But now, if I just jot down the answer key here, 75 degrees Celsius is equal to 348 kelvins. Negative 200 degrees Celsius is equal to 73 kelvins. 0 degrees Celsius is equal to 273 kelvins. Negative 55 degrees Celsius is equal to 218 kelvins. 100 degrees Celsius is equal to 373 Kelvin, and negative 5 degrees Celsius is equal to 268 Kelvin. So for each of these, because we were furnished with the we were furnished with the Celsius temperature, all we had to do was add 273 to get to the Kelvin temperature. Now, on the other side though, we're starting at Kelvin and we're going to Celsius, so we wind up putting in X as the Celsius, subtract 273 from each side to get the answers. 36 Kelvin is negative 237 degrees Celsius. 27 kelvins is negative 246 degrees Celsius. 373 kelvins is 100 degrees Celsius. 59 kelvins is negative 214 degrees Celsius. 273 Kelvin is 0 degrees Celsius. And 0 Kelvin, remember this is our absolute zero, is negative 273 degrees Celsius. So for this portion of AIM number 2, we just did some temperature conversions and talked about temperature. Now we're going to move on to calorimetry. So once again, I'm going to ask you to make sure that you have out your reference tables. We're going to be using on the front table B and on the back table T. So make sure that you have that handy. And again, if you're a fully virtual student, I really highly recommend that you go to Google Classroom, and you'll see up at the top there is odds and ends, or first week, it's in one of those two topics, and you should just go to the reference table and print it out so that you have a copy to flip through. So to calculate the amount of heat or thermal energy exchanged, we use a formula, Q equals mc delta T, and this formula, Q, stands for heat. Okay, again, it's all on table T here. Q is on here, and it says that, and actually I always do this, your Q is a lowercase q. I apologize for that. Q stands for heat, which is measured in joules. M stands for mass, which is measured in grams. C stands for the specific heat capacity. Which for water is found on table B, and the specific heat capacity of water is on here, and the unit actually given is joules per gram Kelvin, and delta T is the change in temperature, and all that means is that you need to subtract the two temperatures. They can both be in kelvins or they can both be in Celsius, because since the size of the degree is the same, you'll get the same difference whether both temperatures are in Kelvin or both temperatures are in Celsius. Thermal energy is the same thing as heat energy, and it depends on both the temperature and the mass. So the more massive something is, the more grams it has. If it's at the same temperature, more grams means more heat energy. So for a calorimetry problem, what you'll see is something like what mass of water will be heated from 50 degrees Celsius to 90 degrees Celsius with the addition of 42 joules. They mentioned mass, they mentioned heat, they mentioned temperatures. So we're going to use this formula, Q equals mc delta T. I almost forgot to show you what a calorimeter looks like. And a calorimeter is really just a vessel that's insulated that can hold some liquid. Oops, I got to put it in front of the camera. That can hold some liquid that we would measure and take the mass of, and a thermometer. So by keeping track of the temperature change of the water and by knowing how much water is in here, we can use this Q equals mc delta T formula to calculate change in heat. So now the Q is my 42 joules. The M is my X, and now here's where we're going to go to the reference tables. Because we talked about water, the C is on table B, and the value is 4.18 joules per gram Kelvin, and then my delta T, I subtract my two temperatures. Take out your calculator, plug in each of the numbers where they go in the formula. Q equals mc delta T, 42 joules equals X times 4.18 times 40. On your own calculator do this work. For Regents Chem, you should be using a scientific or a 4-function calculator. The Regents exam will not allow you to use a graphing calculator, so don't get used to using it in this class. So I'm going to do 4.18 times 40, and I'm going to get, oops, I'm on the wrong spot here, 42 joules equals 167.2 x. Divide both sides by what's in front of x. And I get 0.25 grams. Because I was looking for the mass, I had joules, I had temperature, grams is what was left. That's the only unit that didn't have a partner in my work that I started with. So that's going to be the unit for my answer. I'm going to do one more with you, and then you are going to work on a few on your own, and we will reconvene with the answers. So it says how many joules of heat are required to heat 50 grams of water from 10 degrees Celsius to 30 degrees Celsius. Again, Q equals MC delta T. My Q is my X. My M is my 50 grams. My C, because I'm talking about water, is my 4.18. And when I subtract my two temperatures, I get my 20. Temperature unit cancels, grams cancel. My unit will come out in joules. Take out your calculator and do the work. I'll wait. And what you should have gotten as your answer was 4,180, and the unit is joules because we were looking for heat. So what I'll ask you to do now is please turn the page and work on the next questions. Now remember, kilojoules, 1 kilojoule is 1,000 joules, so keep that in mind when you do the next question. And now what I'm going to do is I'm going to pause the video, and everybody should be working independently on these questions. Follow the formula, plug in what you can, use your calculator, write down your answer, and at the end of a certain amount of time, we will go over these questions and at least put the answers up together. Okay, so I am just going to scroll through a little bit for you to check. I'm just going to leave this on the board and I will scroll to what I have. I have answers done, I believe, up to number 6. If you're ready and you've finished up to number 6 and you've checked your answers and you don't need any help, you can go on to number 7. So when doing problems that have a final temperature component, you want to make sure that you solve for delta T and then work on that temperature component after. So it says, what is the final temperature of a 27 gram sample? That means that we are going to solve for delta T. Okay, if they ask for the final temperature or the initial temperature, you're going to solve for delta T, and then use that information. If heat is added, the temperature is going up. If heat is removed, the temperature is going down. So with that, make sure that you're finished with number 7 and number 8, and I'll put the answers up for those after. So for these two, again, because it is asking for a temperature and not asking about the mass or asking about the heat, you want to make sure that you solve for the change in temperature. Then you read, for the first one, heat was added, so you add the temperature change to the initial to get the answer. For the second one, it says that the sample loses heat, so you subtract from it to get the final answer. And then finally, if you are given information about the calorimeter, we know that we can't measure the mass of water just on the table. So you have to measure the mass of the water by using the calorimeter. So whenever that happens, if they give you the mass of the calorimeter when it's empty and the calorimeter plus the water, you are going to subtract the mass of the calorimeter from the water plus the calorimeter to get the number of grams of water by itself. And so my mass in this problem is 14 grams. And remember, you subtract the two temperatures also to get the delta T. So in this case, my delta T is 40 degrees Celsius. So this just becomes a Q equals MC delta T problem with a change in temperature of 40 degrees Celsius and a mass of water of 14 grams. So you can do that one. And then notice in number 10, they ask you for the final temperature. So remember, you're always going to solve for the delta T and then use that in the problem after the fact. You're going to reread and see whether to add or subtract the delta T. So you can see that I was going along, so hopefully you could see the process that was done, and those are just the final answers that I got. The next thing that you will do is you will work on the questions for Aims 1 and 2. They're on the following page, and whenever you work on questions like this, unless it's otherwise noted, if you go to the back page of the entire packet, the answers to these questions are on the back page of the entire packet. However, you should always work on the questions first before checking the answers. So that was Aim 1 and 2. Actually, I think this was just Aim 2 in this video. Aim 1 was a previous video. But as always, ask me any questions that you might have. Feel free to go back and rewatch if you have something that you still have a question about. Send me an email through school email, send me a remind message, and I can help you with whatever you need help with.